the Otis sample handout. Let me actually link that for you. This is the sample handout which is publicly available. So you can look here for problems as well. Uh,
Oh,
uh,
yes, yes.
there will be a non-trivial overlap in the problems there and here, because like the problems I'm using are like usually the go-to problems for this topic. So there will be
Okay.
a fair overlap.
So like go to means starting.
As in like they're very good examples in themselves. So
Oh, okay.
Evan has also used them, and since I have read that handout, I feel like they're also good examples. Okay, so this is the first. In general, NT construct will sometimes feel like combo, but it's, to me, it feels close to combo, but it's not quite there, because like here also you'll have to take leaps of faith and you'll have to also make guesses and all. But here you are like, the way you'll approach combo problems will be way more abstract, like to get the basic results or the basic structure. But sometimes here you'll have to just, the way you'll get results is by number theoretic means, right? Like, so Evan may have put it better. He said locally it may feel like number theory, but overall it may feel like combo, which is a fair thing, I guess. So the first thing we'll look at is the Chinese remainder theorem. The Chinese remainder theorem and the Lagrange interpolation, you'll see, have somewhat of similar flavor of the way we construct the number in there. Like Chinese remainder theorem, how we'll construct k, and Lagrange interpolation, how we'll construct the polynomial. Okay, so is everyone familiar with what the Chinese remainder theorem actually is?
Yes.
Yes.
Yeah, okay. So still, if some of you might not be. So the basic idea is it is a list of congruences that you want to satisfy, and the set of congruences that you're talking about are like basically co-prime to each other, like mod a1, mod a2, mod an, and all of these will be co-prime. So basically, you just have a set of congruences you want to follow, and you want to find a number which satisfies all these congruences. So the first part here is you need to prove that such a number exists. And then the second part is the construct part. How do you find the number? You'll notice you'll so actually just saying that a number exists is actually pretty easy. Does anyone know how we can say a number exists?
So first of all, if we prove for like suppose only two, like k congruent to b1 mod a1 and k congruent to b2 mod a2, if you prove that there exists such k for these two only, like it is obvious that it will exist for all. We can first assume that, and then we can let k as m a1 plus b1, and then it will be like m a1 congruent to b2 minus b1 mod a2, and
Right.
then existence of inverse makes it true.
Okay, good. So what you basically did is correct. You just tried to construct it though, right? You just want an existence proof for now. And you did it inductively. I want a direct way of just proving existence. Okay, so how we do existence, just existence is, we'll say how many congruences are there mod A1. How many congruences are there mod A1? Just A1, right? 0, 1, 2, A1 minus 1.
Yes. 0 to a1 minus 1.
A1 congruences are there. Mod A2, there are A2 congruences, correct?
Yes.
Yeah, right.
Yes.
And so on. So there can be at most A2 C dots AN congruences, correct?
Yes.
But now if some two of these were same, like between 1 to 3, A1, A2, AN, some two were same, then like A, comma B were both satisfying some set of same congruences.
Yeah,
Then
they will be congruent to 0.
then A minus B is congruent to 0 mod everything. So A minus B, A1, A2, AN divides A minus B.
Yes.
But this is not possible because A and B are both smaller than A1, A2, AN. So no two things could have taken the same congruences. But there are A1, A2, AN things taking at most A1, A2, AN things. So everything has to be taken at some point. Did you get it?
Yeah,
Okay.
yeah.
Yes.
Okay, good. So that's the basic idea of how to prove existence. But what the other person was saying is more interesting. How do we construct it? So what their idea was, we'll construct it for two and then we'll extend it. But instead, let's just try to construct it in general. Okay, so how would we proceed about this?
Yeah, we can start with the very first one. Like we have k is congruent to b1 mod a1, so k can be written as a1k a1j plus b1, and then we put that k into the second, and we get
Yes,
b1j plus. Yes.
that's kind of inducting, no?
Oh, yeah, yeah,
Kind-
yeah,
Okay,
kind of.
let's just look at it this way. We want a number which is congruent to b1, b2, and so on, right? Bn. I'm defining this tuple naturally as you would expect, right? So, but if I want this, I could just simply do this plus 0, 2, 0, and so on. Do you get what I'm trying to say?
Can you turn on auto compile?
Oh, sorry. Right.
Yeah,
My bad.
please.
My bad. Uh, is it? Its auto compile is on, but it's still not compiling. Amazing. Yeah.
I think we should do it fast, like fast draft.
Yeah. Okay. So now this is if we could set it up. If we could find a number which satisfies b1 0 0 0, and we could find a number which satisfies 0 b2 0 0 0, and so on, and we can just then add all of them, right, to get the number which satisfies all these congruences. Then we don't need to bother with all of this. Correct?
Yes.
Okay, so great. We have enough structure to go on. Now, if we can just do it that way, then we just want to construct B100. Is there something in the chat? I can't check the chat, so if it would be better if someone could speak up.
Yeah, there is a raised hand. Like,
Okay, whosoever it is, just
Oh, that was by mistake. Sir.
okay. So then we just want to construct B1000, right? How do you construct B1000?
Take anything that's B1 mod A1, multiply it by the rest.
Close enough. You would need A2 C dots n into some constant, and then you want it, and you then want it to be B1 mod A1. But this you know you can do, right? you can find such a constant. Just take b1 into inverse of a to an. Good enough?
And can you just repeat the last thing you said?
Yeah, okay. So we just want constant into a to an to be equivalent to b1 p mod a1, right? If we want to construct b1 0 0 0 0.
Oh, yeah, that's fine. Just after that, what you said.
Yes, so we can set constant into constant is equal to inverse of a2 c dots n into b1. Right, you know inverses exist, right? If these two things are co-prime.
Yeah.
So yeah, we can just set this now and we're done.
Hmm.
Okay, fine.
So that's how the construction usually goes. Now, what is interesting is this idea that we came up with. If we want to satisfy some conditions for n things, maybe we break it down into small parts for each thing and then add all of them up. It's an interesting idea that will actually repeat in Lagrange interpolation. Can someone explain how we can do it in Lagrange interpolation? Oh, first of all, is everyone familiar with what Lagrange interpolation is?
Can you explain it?
Yes. No.
Okay, yeah, okay, good. So Lagrange interpolation basically says that if you have some set of values, like if you want a polynomial, you can impose n plus 1 conditions on an n degree polynomial. Let me put this way. Yeah. So if you want p of x1, p of x2, and c dots, p of xn plus 1, if you fix where these are some constant x1, x2, xn plus 1, then you can find such an n degree polynomial. It's a unique n degree polynomial, in fact. Okay, at most n degree.
So will that be basically x minus x1 times x minus x2 times dot 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 x minus x of n plus 1, right?
Almost, yeah. You're on the right track. So what you were saying is, like, if we want some conditions like p of x1 is equal to a1, let's say p of x. Okay, did everyone understand what Lagrange interpolation is saying?
Yes.
Okay. So if you have these sets of conditions, and let me just make it see dots. So as before, maybe what we can do is we find a polynomial a1 0 which takes values a1 0 0. Then we find a polynomial that takes value 0 a2 0 0 0 and so on, and then we just add all of them up. Good idea, right? From what you've seen before, it looks like a good idea.
Yes.
Okay,
Yeah.
and how do
Follow
we and
CRT.
how yes, how do we set up this polynomial? Okay, first of all,
X minus a1 times x minus a2 times dot 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 x minus, right?
x minus x3, x minus x2, and so on.
Yeah. Yeah.
Oh, yeah,
Like
sorry.
X. Yeah. As you have written just.
X n plus 1, yeah. Now, what do we have otherwise? We have some constant, right?
Hmm.
Now, all you want is if you plug in x1 here, you'll get some, this will take some value, right? When x equal x1.
Yeah. And
Let,
otherwise it will just be zero.
yes, okay. Let's say this is q. Then q of x, let's say this is q of x. Now q of x1 will be some constant. Uh, Sorry, yeah. Now q of x1 is some constant, right? So we can just
Yeah, yeah.
take this a1 frac, sorry, frac a1 by q1 of q of x1, and we get our polynomial.
Hmm. What is Q1?
There's no q1.
I mean Q of X.
Q of x I just defined as this polynomial. Uh, okay,
Okay, got it, got it.
x
Yes,
minus
it
x.
is. Yeah, it is a general polynomial, which has which is like x minus x2 times x minus x3 dot dot.
Yeah, and it's degree n, right? So we just set p1 equal a1 upon q of x1 into q of x. And that works, right? It gives us the value 0 for all others. And for a1, sorry, for x1, you just get q of x1 divided by q x1, which is 1 into a1. And it works. It satisfies all our conditions.
Yeah, for being a polynomial.
For being a polynomial, right? And we wanted it to take a1 0 0 0 0, which it does.
Yes, and we can just continue this, like by taking 0 8200 and then 008300.
P of 1 is
What?
P1.
I don't get the question. What are you asking?
Yeah, like what's P1? Like P1 is just even by Q of x1 times x1, is it?
Yeah, yeah, yeah. This is a polynomial that we wanted, right? Which satisfies a1 0 0 0 0.
Oh, okay, fine, yeah, fine.
Yeah, and we can add p1, p2, pn plus 1. And as all of them are at most 10 degree, the resultant polynomial will also be at most 10 degree. So we are done.
Yes, pretty clear.
Yeah, so basically we just applied CRT with polynomials.
Kind of, yeah, exactly.
How did we show uniqueness?
That is left. That is what I was going to ask you next. Uniqueness idea is also same as before.
Polynomial with the least degree would be unique.
Let's say p exists and q exists, right? Which satisfy these conditions. P and q, let's say r and s actually. R and S satisfy. Then we do the same thing as before. R minus S takes 0 0 0 0. Right? But then it has n plus 1 roots and is n degree. Must be zero polynomial. Yeah, that's it. We're done. Is this clear?
Yes, yes.
Okay.
Yeah, it's fine.
Yeah, so these two had the same idea, you noticed, right? This construction idea is actually very common. You can try this in the EGMO TST that I've given. Okay? This problem is quite nice and instructive for this type of construction, I believe.
We are doing it right now.
No, no, no. You're supposed to do it later. Okay, now let us look at some other types of constructions. Have any of you seen any of these four examples before?
Yeah, I guess I have seen first one, but not the solution, just the question.
Okay, good enough. So the first question, does everyone understand the question?
Yeah.
Yes. Yes.
Okay. So let's say we have a list of, we want 2015 numbers to take the same value of phi of n. How do you think we can go about this? Any ideas? There's a very smart solution to this, and I don't think that smart solution is so hard to motivate here.
We just assume like prime factorization of n and then write phi of n and then we will try something.
Okay, let's say some number was p1, p2, that's pn. So phi would be,
Yeah, I think that like like shouldn't we consider powers also?
oh, right, of course.
Yeah.
Sorry. Maybe we should look at small examples, right?
Oh, I just got a hint from here, like some idea. Shall I tell?
Yeah, yeah. Go
Like
on.
we have terms p1 alpha 1 minus 1 and p1 minus 1 of this format. So like 2 and 3 have difference 1 and they both are prime. So like we can work with 2 and 3 more.
Okay,
Remains
interesting. And how would you push that?
uh, something if we have 2 to the power 10 and maybe 3 to the power 8, and then it will be 2 minus 1 into 3 minus 1. So it will be basically 2 to the power 11 and 3 to the power 8. And now we can change it to, oh, okay,
Okay.
the power of 3 doesn't work.
I think there will be a limit to how much you can push this. I don't
Yeah,
like, I think you'll need to involve more primes, no?
yeah.
Okay, so if we took a weird thing here, like how do you even control this value right now?
We can take two primes, P1 and Q1, such that P1 is congruent to 1 mod Q1, and then P1 minus 1 would be divisible by Q1, and maybe we can do something with that.
That's a great idea. But the issue is maybe there are more primes, right? Like other primes than Q1 as well. You may not necessarily be able to find Q1 square plus 1 or
pick every prime that divides it.
What if you just pick all primes less than it? Some will work, no?
Less than which?
Let's say the largest prime you were picking is Pn. Okay. In the in this factorization, let's say Pn was the largest prime. Then let's just pick all primes less than it. Isn't that better for us? Like you wanted Pn minus one, the divisors of Pn minus one, right? And then you also wanted divisors of Pn minus one, I assume.
So why are we doing this? Can you just tell it again?
Oh, people are saying that if you have Pn, here you have Pn minus one, right?
Yes.
So maybe if we already had Pn minus one here, then maybe it could go to Pn minus one if all of the prime factors were already here. Like it does not get disturbed.
Okay.
Like, okay, let's say we had Spn as a number and S into Pn minus one. Then phi, where Pn is the largest factor, larger than all prime factors of S, is equal to phi of S into Pn minus 1, correct? And phi of Spn minus 1 is equal to phi of S into Pn minus 1 if all correct.
So like we are just explicitly trying to construct the number.
Yes.
Uh,
Does this make sense what I just
What do
wrote?
you mean by RAD Pn minus one?
Just the set of prime factors, like the product of all prime factors. It's called the radical of a number. Radical of n is just the product of all prime factors taken with multiplicity 1 instead of their current powers.
So of that number is
oh,
P1,
okay.
P2, Pn.
Yeah, yeah. Does this make sense? The last line I wrote. This is what you were trying to come down. You were all trying to say, right? If I'm not wrong. Or this was kind of close to your idea. So I was saying, if we want this, why don't we pick S to include P1, P2?
What you have done is that what we have done is that we have taken all 2015 primes.
We have not done anything yet. We are trying to come up with ideas on how we can do it.
Oh, okay, okay. No, you said that uh, taking small primes. What you said about that? Can you please?
Yeah, okay.
Okay, so yeah, so
Yeah, go ahead. Somebody was saying.
yeah, I think that we're connecting primes,
Okay.
like we're connecting phi of p of n and phi of p of n minus one, right?
Yes, kind of. Kind of. So okay. So what you were trying earlier was saying for p and p1 minus 1 we could have, and then we could have similar phi's, right? Because this is true, what we just wrote. So I said if we could take S to include p, like all primes less than pn, then it would just work, right? Then the radical obviously will have to divide. Then you don't have to worry about which prime you have picked, which prime you have not picked.
Yeah, yeah, right. Product of all the primes will divide S.
Yes, so that would be good enough, right?
Yeah.
But don't you think that like we have to prove it in a context if we are like writing it?
What do you have to prove? Like this statement?
Yeah, this one.
Yeah, of course. This you can prove directly. No, there's nothing much to left to prove.
Oh
Yeah.
Uh,
yes.
S and Pn are co-prime, so this statement just comes by multiplicative nature of phi. And here, if all prime factors of Pn minus 1 divide S, then phi of S includes all of it. So Pn minus 1 does not get disturbed. This you can prove. There's not much to prove here in this statement.
Yeah, okay, fine.
Yeah, okay. Now that you have this, somebody just basically said the proof. I don't think they realized it though. So if we take P1, P2 to be all prime, like let the set of primes be P1, P2, and so on. If we took the number P1, P2, P3, C dots, P 2014, let's say.
Oh, like what I said, taking all small primes.
Yes, if we took these 2014 primes
Oh, okay.
and replaced Pi, any Pi,
With pi minus 1.
yeah, and that just
Oh,
work.
oh yes, yes. And then we multiply all those. So that no.
No. Like P1, P2, P2014 has the same phi if you replaced any P with Pi minus 1, right?
Yeah, by the multiplicative nature.
Yeah, by the thing we just proved, or by the
Yes.
thing we just said.
Yeah. Okay.
Because S includes all primes less than it, so it includes all prime divisors of P1 minus 1.
Yeah, fine.
So we have 2 and 14 options. So 2 and 4 options, and 1 is the number itself. We are done.
Can you again tell what S was?
Oh, in this place, in this case, S
Yeah,
just
so
represents.
like S is any integer, right?
S is any integer such that radical of Pn minus 1 divides S.
Oh, okay, so this is our condition, not like a consequence.
No. This is our condition when then only this result follows, right?
Yeah, yeah, that's why I was confused till now. Yeah, so this is a condition. Okay,
Yeah.
fine.
I wrote if no.
Yeah, okay, fine.
So
P1.
I guess now all the things are clear. So what we do is we just take small 2014 2015 smaller primes, and then
Yes.
we just multiply them all, and then replace each pi with pi minus 1, and then take 2015 numbers, and we see that all the numbers are the same phi.
Yes. Exactly.
Yeah, okay, so like, the crux of this problem was to figure out that phi of SPN equals phi of S times P of N minus 1, right?
I think there are two parts. Like first, like this observation, and the second part is you can extend it to this type of structure. You can just pick such primes easily.
Yeah, okay, so if I understand the solution right, so what we did is we consider a number P1, P2, P3 or till P24. So this is one number, And now what are we saying that like if you consider if we replace any pi with pi minus 1, then the phi of that number will remain same. So we got 250 numbers such that phi of n equals like same. Phi of
Exactly.
all these numbers are same.
Exactly.
Okay.
Make sense?
Yeah, totally.
Yeah, yeah.
I
Very,
think this.
very, a very good example. This was
Yeah, 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 I like it a lot.
like 2015 is a quite big number.
Yeah, it's just because it was given in the year 2015. That's all.
Yeah, yeah. That is
I mean, you can extend it arbitrarily, no?
yes.
Like I think that if we like if we replace 2015 with any number, it will work.
Yes, yes, of course. These numbers are usually just to give the year. It,
Yeah,
Yeah,
in
yeah.
most cases. In most cases.
yeah, or like they'll have some special property, like it's a prime or something,
Yeah.
but barely. Okay. Now on to the next problem. Was the
No,
motivation clear here?
I have a doubt in that problem.
Yeah, yeah.
Like after that, in the last line when you constructed it, like P1, P2, P1, P2014, and then you write at last S equal to P1, P2, so on till divided by Pi. So like, why did you put it that?
To explain this, like to compare it to the previous thing, like for the people who were getting confused how S is here, I just try to explain it like you're replacing pi by pi minus 1, right? So that's basically the remaining number which we did not edit is S. That's all there was to it, nothing more.
So product of all the prime factors of Pn minus 1 will divide this S, you mean?
What do you mean?
Product,
S will divide the yeah product. Yeah, okay, yeah, you were right. I'm sorry.
okay, so
It's just because all primes less than pi minus 1 are in S.
yeah,
So
yeah, yeah. Okay.
yeah, okay, good. So now that we have that, let's look at the next problem. Actually, let's look at the RMM problem first. This was actually quite famous, and I'm surprised you have not seen it before. But let's try the RMM. Okay, so rather than finding such numbers first, anything you observe directly, let's say.
Yeah, directly we can observe that we have a theorem that a plus b divides a to the power n plus b to the power n if n is odd. So
That
uh,
n to the a plus 1 divides n to the b plus 1 if a divides b is what you meant, I think.
yeah, yeah, yeah. So here also that we like we need that n divides 2 to the power n plus 1.
Yes, perfect, actually. So if n does not divide 2 to the n plus 1, then what can we do? Okay, if let's say there's a number n that satisfies the problem condition, can you get another number that satisfies the problem condition?
Oh yes, yes. We have to construct that another number.
Yes, can you get another number if you have a number?
If we have a, then we can let b equals a times something.
No, no, no. From the problem structure only look at it. Don't try to
Oh, okay.
go beyond.
Yeah, so what like, like the first thing that comes in your mind is consider 2 to the n plus 1 as x.
Okay.
Yeah, so like we need to prove that n there are infinitely many n's such that n divides 2 to the x plus 1 and x doesn't divide 2 to the x plus 1, right?
I don't quite follow.
Yeah, so let me repeat. 2 to the n and plus 1, let be x.
Okay, let's say
2
I'll
to the
define it as
n.
f of n is equal to
Oh,
2.
yeah, okay, fine.
Okay.
Yeah, so what we need to prove is that there are infinitely many n's such that n divides 2 to the power f of n plus 1. 2 to the power f of n. Oh, yeah, fine. But not f of n divides, but not n,
Yes, this is what you're saying, right?
but 2 to the n plus 1 is not. Uh,
Yeah, but n not.
oh, yeah, fine. Yeah, fine.
Okay, so I think somebody just said the idea first, but they missed how we have this property, right? X to the a plus 1 divides x to the b plus 1 if
Yeah, yeah, yeah.
a divides b and both are odd. Correct?
Yes.
Now, what does this not mean n divides f of n if
How one proved this?
and oh, this lemma that I just wrote.
Yeah, yeah, this one. X of a plus 1 divides x of.
Easy, easy to do.
Oh, okay. So I'll just prove this.
Yeah, we can just write minus minus one in bracket and then
Yes.
just apply the
Uh,
theorem for minus.
Euclid division algorithm basically. F is equal to ak plus
Yeah,
r
that is another way. Yeah, we can also prove like that.
implies x to the a plus 1 divides x to the uh, ak plus 1. This is fine, right? This you just know.
Yeah,
Sorry, this is plus 1 here. This implies x to the a plus 1
divides x to the
ak plus r
r. Yeah.
plus
And
a plus x to the r implies, if the other thing is true, then uh, x to the a plus 1 divides a to the
yeah,
r.
so like these type of short lemmas, we have to prove it in move. Else we won't get marks, right?
Yeah, you have to write this, of course. But like, since this is informal, you don't need to. It implies r equals 0. Okay? This much is fine, no?
Yeah, this is fine.
Okay.
Yes.
Now, since you have this, uh, okay, this is just, I don't know why. Okay, so do you see this now? N divides f of n if and only if f of n divides f of n. N divides f of n implies f of n divides f of n. Do you see that?
Yes, yes.
Yes, yes.
Okay. And do you see why f of n divides f of n implies n divides f of n?
Yeah.
Yeah, so if n satisfies our condition, so does f of n.
Shouldn't n divide f of n?
No, it says
Oh,
if and only if, right? So if n does not divide f of n, then f of n does not divide f of n. And if n divides f of n, if and only if f of n divides f of f of n. Right. Okay, so that is, so if n divide, if n satisfies a condition, so does f of n. Is this clear?
Yeah.
Okay, great. Now comes the main part. How do you just need to find one number now, right? As soon as you find one that satisfies problem, you're done, because you can find n implies f of n, f of n, f of n, and so on.
Oh, okay, okay. Okay. So like A implies B, B implies C, C implies D, and this goes infinity.
Yes.
Can you just please repeat the argument, like how
I
to be
think
written?
three. I think three is the number.
3 does not work, no, because 3 divides 9.
Oh,
Archie, can you
Yeah.
just tell again, like how n divides f of n is same as n dividing f of n?
How n dividing?
Like, why did you consider n divides f of n? We have to find n divides f of n. No?
I mean, if n does divides f of n, then f of n divides f of n, right? It's an if and only if. So n
Okay.
does not divide, then f of n does also does not divide. But you're close, no? Like you, let's if we start. Uh, so 3 does not work. Somebody said, right?
Yes. 3 does not work. Yeah, because 3 divided 9.
But it's fine. No, if 3 does not work, but what about multiples of 3?
Yes. Yeah, we can. Like 9.
No, 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 no. Don't go
9.
that abstract. Like, just don't start guessing. Like, look at the structure.
Yeah, yeah.
We had n does not. Okay, so if we were replacing with 3k, right? We would want, let's say 3p for some prime, right? Want p not mid n mid 2 to the 3p plus 1, or equivalently 2 n mid 2 q plus 1, right? The
Yes.
plus 1 implies p not equal to 3. What's the other condition? And we want 3p to divide f of 3p, right? We want,
Yes.
but
How is that equivalent?
I
We're
mean,
not dividing 2 to the power 3 plus 1 equivalent to we're not dividing 2 to the power 3 plus
mod p, if you look, we know that 2 to the 3p minus 3 is congruent to 1, no? Fermat's little theorem.
1.
We want this, but we already have 3 works, right? So we just want p does not divide. P divides, sorry. We want, correct? This
Yeah,
is
yeah,
what,
correct.
okay. So now we just can finish. Observe that f of 3 divides f of 3p. because this should be f of 3 divides f of 3p, and thus f of 3 divides f of f
Yeah,
of.
like yeah, this is clear.
Okay, cool. Now if we have this f of
Can
f
you
of
compile it?
oh sorry, I should scroll down. Yeah, okay, sorry. So so we just we can just pick a prime factor of f of 3, and we'll be done, right?
Yes, makes sense.
Yeah, and now you can, now if you actually want to find a number, just say f of 3 is 2 to the 9 plus 1 is equal to 513 is equal to 9 into 57 is 27 into 19, so equal 19.
I
So
think Fermat's little theorem is applied showing things here.
what, sorry, just a second. Hi, very sorry, I'm back. Did someone say anything?
Yeah, so I was saying that I think Fermat's little theorem is applied too many times here.
Oh, when? Otherwise, have we implied? I think I sometimes I just use it without thinking. So
Yeah, so like yes, like that comes after too many experience, too many practice and experience. But like these are things are not too obvious. So
right,
I
you're
think
right.
yes, like can you tell the like can you tell that if any theorem is applied here every day or something?
I really don't think so. I think just here we implied use the theorem, Fermat-Slater theorem in this step, and otherwise we used this lemma that we proved for this step, for this step, for this
Yeah,
step,
fine, fine.
for this step, for this step, for this step. This lemma we used all everywhere because the crux of this problem is this lemma, but I don't think we used anything else.
Oh, why did you write we can just pick a prime vector of f of 3?
We can, like, we wanted 3p, right, to work, and we
Mm-hmm.
wanted p to divide f of 3p,
Yeah.
but f of 3 divides f of 3p.
Yes. Okay. Okay.
Yeah, okay, cool. Yeah, okay, since okay.
Isn't like construction thing more very abstract to think such way?
Sometimes, yeah, but like that's why I said almost it's almost like combo, but the steps you'll be doing are NT type because these ideas n divides f of f, and these steps are NT.
Yeah, so I think that the crux was to the thing that led to it, like apparently,
What?
like that
Uh,
considering f of n. Like after
the
that,
crux of
like one can start deducing stuff. isn't it?
Yes, but I think like
That
sometimes
that
it's
lemma
just
is.
like the first thing one of you said, I don't know who, was this lemma, no?
Yeah,
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 So,
yeah, yeah.
so you were able to
yeah.
identify that this lemma is important without even
Yeah,
knowing anything about the problem.
right, right.
Yeah, so I think that there were two crux. First was this lemma, and the second was the first line. Like, isn't it?
You mean this thing?
Yeah.
Yeah, okay. Yeah, I think that's fairly important. Now, okay.
FFN was notation. Like,
Oh, yeah, that is just for notational purposes. You can say if n works, then 2 to the n plus 1 also
yeah,
works. And
yeah.
then
We can
this,
just write that.
yeah, but for if you want to properly write it and want to make it really nice, you can say f of a divides f of b. If a divides b, a divides f of a divides f of a, and all that stuff.
Mhm. Yeah, yeah.
So, like, will this solution fits like anyone 7 out of 7?
The way I've written it,
Yeah, yeah, yeah.
I
Like
don't.
this whole thing.
Uh, on a usual contest on Inmo, no. He'll need to explain, no.
Yeah.
And I am
At IMO, it might.
okay. So, like, this means that we can skip obvious steps at IMO. No
Uh,
one cares about it.
no, at IMO, they are you have people arguing for you.
Oh, okay, okay.
The team leaders basically, you mean?
Yes, they if the other person does not understand sometimes, they can help explain. But if the other person still might judge that you missed something obvious and still might cut marks. I got 6 on 2 problems for this exact reason. I missed some really silly details, and they were like, "No, we'll cut marks for it."
It's a scam.
Oh, okay, so like at IMO, you have the power to discuss like your answer sheets with the uh, yeah, go
Even
ahead.
at even at team selection test, you'll have that power.
Okay, but not anymore, right?
INMO is just too large a scale. No, you have thousands of 1,200, kids writing it.
Okay,
It's
yeah,
just
fine.
not
But you
possible.
can apply for RTI in Inmo, no?
I mean, you can still not argue. No, it's
Ah,
just say just recheck is all you can say.
Yeah, okay, so I think that at IMO this solution is fine, but at INMO we need to explain each and every step.
Almost each
Like
and
what's
every step, like everything which is slightly non-trivial, you need to explain at INMO also, at IMO also. At IMO you might get leeway. At INMO you will not get leeway.
Yes, because the point is just to explain, and this really lacks some exposition little. So
Yeah.
yeah,
Yes.
right. We have to just organize this. All the things are here.
Yeah, exactly.
I don't see where's the problem to not write everything.
Yeah, really. You can just write it, it's fine. You have enough time in both tests. Okay. Sometimes you may miss details unintentionally. You might be like, this is obvious, and it may not strike you to write it. That's another issue.
Oh, anything can happen. Right.
Yeah,
Yeah,
okay.
this is
This problem I'll leave as an exercise. Is that okay?
yes, yeah.
Okay. Has anyone tried this problem?
No.
Okay. So do you understand the problem?
Let us read first.
Yeah, of course.
there are two parts of the problem, right? Which one are you gonna do right now?
There's just one part of the problem. I don't know what two parts you refer to.
No, prove that every integer x greater than or equal to 2 can be written as product, and then there is
Right. The first part is actually fairly obvious. You'll not
yeah.
need to prove it or anything. The main thing is the second part.
Can you explain the second part of the problem?
Okay. So do you understand what f of x means?
Oh, yeah.
From the first part, we are implying that every number can be written as a product of one or more elements. So f of x is saying what's the minimum number of elements you need to write x. Now,
Isn't the statement of using like x can be written as product of f of x elements of A?
but you need at least f of x elements, and you can do it in f of x elements. And you need to show that f of x is defined. So that's the first part, that f of x is defined. F of x exists, right? Because,
Oh, okay, fine, fine.
and then the second part is saying f of xy is less than f of x plus f of y holds true for infinitely many x and y.
Also, like for all and for infinitely many, are these two things different?
Very, no.
Yeah.
Infinitely many, there are infinitely many. Okay, all integers are not even, right?
Yeah, but there are infinitely many variables.
Yeah, 50%.
Sure, let's say that. Yeah,
Apparently 50%.
yeah. Okay, so this is an interesting problem, and it's not that hard either. So let's look at it. So first part, how do you do the first part? The first part is actually something you have all done before, I'm sure.
It's like Simon's trick.
Simon's trick?
I mean, you know the
Adding
form of
plus one to both sides.
Nothing like that, dude. Come on. You
It becomes
just
like 4 by 2, 5 by 2, 6 by 2, 7 by 2, and it covers all that.
Wait, can't we
Yeah.
just do 2 into 3 by 2 into 4 by 3 and see
yeah,
what
exactly.
exactly, exactly.
Oh, yes, yes.
Uh, uh, k by k minus one and so on. This gives you k plus one. Okay, f of x is defined. Brilliant. Now, now let's look at the second part. What thing would you want for this? When would you expect this to fail?
When the function is not eh, no.
RJ, can you just explain like f of x definition once? Like,
You can write every integer as a sum of some elements of a, right? That's the
yes.
first part.
Yeah.
What's the
Definition.
minimum number of elements of a that you need to multiply to get x?
Oh, okay. Okay.
Like obviously these are distinct, right?
Not so, which are not necessarily distinct.
Okay. Okay, okay, okay.
f of a
If
prime
we
is
write xy is like whatever we write for x multiplied by what we write for y and then try to combine some terms.
Good, but like, okay, when do you think f of x and f of y would need large values, but f of xy could be very good? Okay, let's say what numbers need very less terms for their values that you would expect according to size that they would need a lot of things but they don't.
So basically, which has so like shortest will be if k plus 1 is divided by k minus 1. So like it has
K
many
plus
divisors less than it. I
k
mean,
plus
like if we write k
ah,
plus
right.
1.
Of course. So you're right. Just a there must be many twos, right? Is what you're saying.
Yes, I know.
Okay, but 2 to the a you can't go. 2 to the a is bad because all divisors are 2 to the b and 2 to the c, which is just good enough. But what, just add some slight thing and you're happy. 2 to the a plus 1 is very good because you just need a plus 1 terms. Correct? Hello?
Yeah, correct.
Yeah.
Which a plus one terms? Can you please explain?
Uh, f of 2 to the a plus 1 is a plus 1, right?
Oh, how though?
How
Uh,
is that?
I mean, okay. 2 to the a in times 2 to the these are 2 is there a times and then 2 to the a plus 1 upon 2 to the a.
Oh, okay.
Okay, they can't be distinct. Yes.
They can't be distinct. They're not necessarily distinct.
Yeah, I mean.
Yes, so this is very good. Now, if you had some prime divisor, okay, so can everyone see that if there's a number x, then you need at least scaling log x term. Does everyone see this?
Yes.
Right. So now this needed exactly a plus 1 terms. Now let's say it has a prime divisor 3. It has prime divisor 3. Yeah. Then 3 itself needs uh, 2 terms, correct?
Yeah.
And 2 to the a plus 1 upon 3 also needs at least 8 terms.
Yes.
If you're done. That's it.
Oh, right.
We don't need to do anything more. That's it.
Like, how can these problems are seen to be easy now?
What do you mean?
Like, they have big names, IGNO TSC, problem number 6. They seem to be easy now.
I mean, two things. One will come with experience. Second, they're all supposed to be very solvable, no? They're not, Olympiad problems are not supposed to be like unsolvable or something.
Yeah.
They're all supposed to be solvable in reasonable amounts of times.
So, like,
Except
do
for
you
x.
remember that? How much time did you take to come up with the problem for this solution?
2
Like, how much time did you take to come up with the problem for this solution? 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon 2 to the A. 2 to the A plus 1 upon
This solution, I think it took me 10-15 minutes.
The previous solution took 2 minutes, by the way.
This one, yeah.
Yes, previous was because of the lemma.
Yeah.
And the
Mm,
first one?
This one I don't think I did on my own. I'd seen the solution.
Okay.
yeah, in the
So
first
like,
one, the construction can was not very easy.
No, also it's been a long amount of time.
Yeah,
I
yeah,
mean,
that is also right.
so like in the meanwhile time, I asked like in the leftover time, like can you just motivate the solutions, motivation of the like other problems, like generally,
uh, motivate which problems?
like generally all like.
I mean, okay, look at what we were doing here only. So in the EGMO problem, we said, okay, we need f of xy to be smaller than f of x and f of y. So maybe let's look at cases where f of xy is just very small. No. So the first case is 2 to the a, but 2 to the a can obviously not work on its own because all of its factors are of powers of 2 and all. So then we just took the most natural thing and we added one term, 1 to it. And that just works because it's very close to awesome. So it just works.
Okay.
Here, I think you just need this observation. It's not that hard an observation, to be honest, but you need it, yeah. Otherwise, also, you just need to look at the structure sometimes. Sometimes small cases will help, sometimes they won't. Here, I think small cases are actually useful if you do case of 5 or 6. But this is slightly tricky. You may, yeah.
Yeah, tricky.
Again, in this, you have the general construction ideas, no? Okay, let's look at the example problems that have given you. We try to get ideas from what we did here. It won't work directly. It's a fairly different problem, and I think harder, not much harder, but I think harder than the RMM.
Yeah, like because examples are supposed for that.
No, 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 no. I just think this is a good problem, and you should try it.
No,
It's
like you said that try to apply the ideas which are in the examples. So that's what I said. That
yeah,
examples are to illustrate ideas.
yes, yes. Also, this one is a very good example. I really like it as an instructive problem. Do try this one. Uh, I have a solution on the thread if you want to read it later. Uh, Other than that, I think these are good problems. Okay, let me open the other handout, which has the bigger set of problems. I mean, they're supposed to all be solvable. Not all of them are.
Like, can you also tell that what are arrows?
Arrows, I just mean iterated FEs, for example, where you're talking about reapplying the same type of function again and again.
Okay, so like NT plus FE.
Kind of, and sometimes permutations or other things, like where uh, we are kind of saying A goes to B, B goes to C, and then we are trying to create some structure of that sort. And then you can say there's an arrow from A to B, and you can it's helpful to visualize and think about the structure. That's all it is.
Okay.
Oh, right. You should. I forgot to give this problem. Do try this one in particular. Uh, from 2019 ISL, I think. Rootiful something something. Does anyone know the name? Like the number, I think N3.
2019 N3.
Yeah, N3. Do try that one as well. It's a slightly different idea, and with okay, 2020 N4 is also good. Okay, I'll just send you a list of problems to try then. I'll try to compile one today. Anything else? You can ask.
We are not gonna do any other problem.
I don't think we have enough time.
So I think that we can try these exercises from this handout, and this will use what we did today, right? Like
Right.
any case you think that like any sentence which can motivate some of these exercises, it will be good.
Right. Okay. I mean, there are five problems we have not done from here. I'll just extend. This is a problem section here, right? I'll extend this section to include easier problems as well, and some hard ones as well. And I'll just clean this up, the previous parts we have done, and I'll send it to you all. That's fine,
Yeah,
right?
okay, fine. So like, yeah, so yeah, so what I think that in the meanwhile you can like send this so that we can try these problems right now.
Ah, of course. Yeah, I'll just
Like just
send it.
send
And
this draft first, yeah, and then you can modify it accordingly.
yeah, yeah, okay, sure, I'll do that.
Do you have like
Also, just
something?
half a day, so like it's fine if you don't send it immediately. Also,
No, I'll just send this current file, and the updated file I'll send by at night after my lecture.
Do you have something for 5 to 15 most number theory?
Uh, okay. Firstly, stop being scared, man. I've seen in general you are very scared of problems. Don't be.
I'm just scared of number theory.
Yeah, yeah. Especially number theory. I've seen a lot of you are. Just don't be. Uh, I mean, we did the problems right now, right? They were P2s and all. They were not so hard.
Yeah, P2s and P5.
Yeah.
I think number theory can be like motivated, but geometry and algebra are like rigid.
Uh,
geometry.
I again varies from person to
No, no,
person.
no, no, no. I think that if one hasn't done geometry and one hasn't done number theory, one can still motivate number theory solution, but one cannot motivate like geometry anyway. Like, did you get my point, Atul?
Yeah, I got your point, but I don't know how true that is. Uh, I think like for a new person who has not seen much number theory, it will be hard.
Yeah,
Okay, uh, yeah, okay. These two problems also you can try. 2019 N3 and 2020 N1. And if you're looking, the ones who wanted slightly easier ones.
so like whenever you send this draft handout right now, just like yeah, so just like type these two or three in the like chat or in that thing
Yeah, yeah.
anyway.
I'm just sending a draft right now. I'll add these problems and others at night only.
Yeah, okay, fine, fine. Yeah, so I will practice these right. Okay, fine. Send. Okay. Yeah.
You also just rest because you have many lectures after this at night too.
Yeah, yeah.
The 2020 N1 uses construction.
Kind of. I mean, you can club it with construction. For example, two to the like even
Don't
strictly
spill, don't
speaking,
spill, don't spill.
I'm not telling you the solution. Don't worry. I'm saying
Okay.
strictly EGMO problem is also like we are clubbing under construction, right? So similar things we club under construction together only.
Okay.
Okay. I hope you'll enjoy it and I hope you learned something.
Yeah, very much enjoyed.
Okay, nice. Okay, see you all
Yeah,
at
thanks for the lecture.
Yeah, great session.
yeah, see you all in the evening.
Yeah.
Okay, what somebody raised their hand?
Not as a
Okay. Oh, okay, okay. Thank you. Bye.
Thanks
Bye.
for the session.
Bye.